All right, so today we are going to be talking about the fundamental theorem of calculus. I've always liked this section because honestly, I just love the name of this. It's a fundamental theorem, and it's the main concept that calculus tries to drive home. When I first taught calculus, it made me wonder, well, how many fundamental theorems are there? There must be one for every level. And that's when I started to do a little research. And yes, I'm going to use Wikipedia, but it just wanted to show you that there are a lot of fundamental theorems for different things. So some things that might be applicable, and what these are is they are rules that are supposed to connect concepts. So the fundamental theorem of calculus, this says that it is a theorem that links the concepts of differentiating a function with the concept of integrating a function. So we are going to be combining the two concepts that we've mainly focused on this semester through the fundamental theorem of calculus. Some other ones that you have used, and you may not have known that it was a fundamental theorem, there is a fundamental theorem of arithmetic. For those of you that have wondered why 1 is not a prime number, because it's supposed to be multiplied by itself and 1, it's not a prime number because of the fundamental theorem of arithmetic. The fundamental theorem of arithmetic states that every integer greater than 1 is either prime or is a product of prime numbers. So because this was created, as you can see, by Friedrich Gauss, since he wrote and published, and it was proven to be true, and it's taken to be kind of mathematical law, he stated that any number greater than 1 is a prime number or a product of a prime number. He didn't say that 1 is a prime number or anything of the sort. So because he did not include 1, that's why even today, we do not consider 1 a prime number. Fun fact, I always got a chuckle out of it, mostly because of the response. I worked at Elm City Brewery years ago, and I was a cook there, a dishwasher, a cook, and then a server. I love the place. It's a blast to work there. And at the beginning and end of every shift, you have to punch in and punch out. And you do that by typing in your 3-digit code. And it's randomly given, and I got the code of 235. So 235, I had to punch in and punch out. I got that. I was like, that's awesome. And then my boss just looked at me and she's like, what's awesome? I'm like, it's the first 3 prime numbers. And that's when you see the look of just like, math. But I always thought that was funny, and I always kind of chuckled a little bit when I punched it in. And when someone saw me punching in, I'm like, yeah, it's the first 3 prime numbers. And I mean, they knew I was a math teacher, but I always got a kick out of it. I was the only one that did, but every time I did. Fundamental theorem of algebra, that talks about it states that every non-constant single variable polynomial with complex coefficients has at least one complex root. So what that is saying is that complex numbers, we've gone over there, that's every possible number that you can imagine. So that includes real and imaginary numbers. And so if there exists a function, then it has to have at least one root. That root can be imaginary because, again, it's a single variable polynomial. So it has to somehow at some point have a root to it, meaning it has to have a solution. And then that is based off of, as well as the exponents and all that jazz. So something that we had done of solving when x equals 0 or the quadratic formula, all those exist because of the fundamental theorem of algebra that states that it must exist. And if it does exist, there must be a way of finding it. So if you had some free time and you want to just kind of go through a lot of cool fundamental theorems that probably don't really make much sense unless you've taken the class, but just kind of, it's kind of cool to know how many fundamental theorems there are. So today, we're going to be talking about the fundamental theorem of calculus, and it's broken down into 2 parts. The first part is a little complex, but then we're going to break it down with a nice picture and then kind of simplify it. And then when we get to the examples, it will make more sense. And then the second part is actually something that we've already done from the previous section. So it won't be too daunting to try these problems. So here we go. This is the definition of the fundamental theorem of calculus, part 1. If f is continuous on a closed interval, a to b, then the function, capital F of x equals the integral from a to x of f of t dt. It has a derivative at every point x in a to b, and so therefore we can say that the derivative of the capital F in respect to x is equal to the derivative of the integral of f of t dt, which that in return equals f of x. See, pretty simple. Just kidding. To illustrate with a picture. So a picture means that we have, not a picture, this picture means that we have some curve and it's going from A to B, and we have some arbitrary value x that is somewhere between A to B. Now, what this fundamental theorem of calculus is saying is that if we wanted to find the area under the curve up unto x, what we would be allowed to do is rewrite the function in terms of x, find the antiderivative of that function, take the derivative of the antiderivative, and we'd end up back with f of x. A little more sense? All right. We're going to say it in more simple terms. So the derivative of an integral is notated as capital F of x when it's in respect to x. Now, if capital F of x is the antiderivative of the integral of that function, therefore the derivative of the antiderivative would bring us back to the integral. Now, if the integral was from a to x of f of t dt, and we're saying that its antiderivative is capital F of x, well, the derivative of capital F of x would be lowercase f of x. So it's kind of like we're finding the antiderivative to then derive it again to bring us back to where we were. But the main difference is instead of it being in terms of t, which the entire function is, we are now rewriting it to being in respect to x. And we have something that we can use and manipulate as long as we are plugging in x. And it could be c, d, r, it could be any variable. But we have the power to rewrite that function to be in terms of the variable we want by simply taking the antiderivative and then taking the derivative again. You don't like that? All right, even more simple. Just rewrite the integrand and replace the variable with what it's in respect to. That's all you have to do. So for example, if I have the integral from negative pi to x, cosine t dt, if I took the antiderivative of cosine of t dt, which would be the capital F of x, so that would be the sine of x, because I'm now taking the antiderivative in respect to x. And then if I take the derivative of sine of x, I get the cosine of x. And so I'm going to get rid of the middleman. I'm not going to do that redundant step of taking the antiderivative and then deriving. I am just going to simply skip that and say, all right, cosine of t dt is equivalent to cosine of x. And I don't have to worry about this lower bound because if that's where it starts, x is where it ends. So then to evaluate that curve of where it stops at x would just be cosine of x. This problem here, if I had the integral from 0 to x of 1 over 1 plus t squared, I am simply going to replace this t with the x, and I get 1 over 1 plus x squared. The antiderivative of 1 over 1 plus t squared is, and it's going to be one of our inverse trig functions, but it doesn't matter because as soon as I take the derivative of that trig function, it goes down into the 1 over 1 plus t squared. And if you're wondering, it is the inverse of tangent. All right, now part 1 can get a little more complicated because we can throw the chain rule in there. So with the chain rule, I would do the same exact process as before, but then I have to multiply by the chain rule. So since there is a derivative of x squared that exists, I have to multiply by its derivative, which would be 2x. So I replace the t with x squared times the derivative of x squared, so I get 2x cosine x squared. Not so bad. Well, what happens if there exists a variable in the lower limit? Well, if I have x to 5, I can use one of my rules. It was the first rule that we had from section 1, And that allows me to flip the lower bound and the upper bound. Maybe it was section 2. I don't remember. I think it was section 2. I can switch the lower bound and the upper bound and then take the negative of the integral. And so now that I have the negative of this integral, I'm going to go ahead and replace the x with the t. This one's a fun function because there's 2 t's to replace. So then it would be 3x sine x. And then don't forget that negative, so negative 3x sine x. Well, what if both the lower and the upper are variables? Well, then we're going to do what we had done in our previous section of finding the values of the two and then subtracting them. So I drew a picture of showing that we have this function from A to B. This obviously isn't what this curve looks like, but whatever. So from A to B, and I'm going to 2x and x squared. So these two values, by the fundamental theorem, have to lie between A and B. And so if I were to find the value of 0 to x squared and find the value of 0 to 2x, and I were to subtract those two values, well, this overlap is going to cancel out, and I would be left with 2x to x squared. So that's the idea behind what I'm about to do. So here's me doing it. So the derivative of the integral from 0 to x squared, I just said 0 because that's a common starting point. I suppose I could have done from a to x squared, but whatever. And so I'm going to go ahead and put in the x squared in for the t. I'm going to put the 2x in for the t, and I'm going to notice that both of them are going to require the chain rule. So make sure you don't forget that. So here we go. 1 over 2 plus e to the x squared times the chain rule, 2x, minus 1 over 2 plus e to the 2x times the chain rule of 2. And then I throw the 2 into the numerator, the 2x in the numerator. I look, they are unlike terms, but there's no point in finding common denominators because it wouldn't simplify our problem at all. So this is our answer. Part 2. If f is continuous at every point on the closed interval a to b, and if capital F, which is the antiderivative, is any antiderivative of f on a to b, then the integral from a to b of f of x dx can be evaluated by taking the antiderivative of f of x and plugging in b, which is the upper bound, plugging in a, which is the lower bound, and finding the difference between the two. This part of the fundamental theorem is also called the integral evaluation theorem. Because we are evaluating an integral, it has been proven to be true, so it is a theorem. This is why we're able to evaluate the integrals using the differences of antiderivatives from the previous sections. So here we go. If I had the integral from -1 to 3 of x cubed plus 1 dx, its antiderivative would be 1/4 x to the 4th plus x. I can double check this by taking the derivative of this, and that should give me back to my integrand. Remember, the fundamental theorem of calculus part 1 says if we take the antiderivative and then take the derivative of it, we are left with an equivalent statement. So the derivative of 1/4 x to the 4th plus 4, bring down the 4, the 1/4 and the 4 cancel out. This reduces to a 3. It gives me my x cubed that I was looking for. And then plus the derivative of x would be 1. So we're good. This vertical line is showing me that I'm evaluating from -1 to 3. So I go ahead and I plug in the 3 into both x variables. I plug in the -1 into both x variables. I start to simplify. I continue to simplify. I simplify. I simplify. I circle because I'm happy. So the answer to this would be 24. So your homework for today is going to be 6 problems. I went through and I picked some of the specific examples that look like each type we did in the fundamental theorem part 1. And then I gave you 2 problems for the fundamental theorem of part 2. One is a trig function. No, let me look. Oh wait, no, I forgot. One is a trig function and one is not. So try those out. Good luck. If you have any questions, come on into Zoom and I would love to answer any questions. Happy Thursday.